Now we connect the characterization of eigenvalues that we just saw with the Laplacian matrix that came up in the statement of the fundamental theorem of spectral graph theory. Remember that we define the Laplacian matrix to be equal to the identity minus 1 divided by the degree times the adjacency matrix, where A is the adjacency matrix of some graph G that is the regular. So now we know that lambda 1, the smallest eigenvalue of the Laplacian, will be the minimum over non-zero vectors x of x transpose Lx divided by x transpose x. And then lambda 2 will be the minimum of this ratio over all vectors x that are orthogonal to x1, where x1 was a minimizer of this ratio, and so on. So we can understand the eigenvalues of the Laplacian matrix of a graph in terms of minimization problems applied to this Rayleigh quotient. But what is this Rayleigh quotient and how does it relate to connectivity and bipartiteness? I claim that the Rayleigh quotient of x is the following expression: summation over all edges of xu minus xv squared divided by summation over all vertices of the degree times xv squared. So let's first see what's the numerator of this expression. So we can expand the square, and so we're going to get summation over all edges of the graph of xu square plus xv square minus 2 xu xv. So summation over all edges of xu plus xv square is going to be equal to d times summation over v of xv square, because when we sum over all edges the value xv square of both endpoints, every vertex will be counted in this summation as many times as it appears as an endpoint of an edge, so d times. Now this difference can also be written as summation over all uv of auv xu xv, because a will be 1 for every edge, but a will also be 0 for every non-edge. So this is the same as taking this summation over all the unordered pairs of vertices, because the unordered pairs of vertices that are edges here will be counted 1 as in this summation, and for the unordered pairs of vertices that are not edges, this will be counted 0 as they were here. Now counting twice every unordered pairs of vertices, it's the same as counting once every ordered pairs of vertices. And so this will be d times x transpose x. This is just x transpose ax. And so this is x transpose times di minus a x, or equivalently it's d times the numerator of the Rayleigh quotient of the Laplacian. Now when we divide by d times summation over v of x for v, using this expression for the numerator, d will cancel, and we're going to have this. This is precisely the Rayleigh quotient of the Laplacian. So the Rayleigh quotient of the Laplacian is this expression, and so lambda 1 of the Laplacian will be the minimum over all non-zero vectors x's of summation over all edges of xu minus xv squared divided by d times summation of xv squared. We immediately see that lambda 1 has to be greater than or equal to 0, because for every choice of x, both the numerator and the denominator will be sums of squares, so they will be non-negative. But if we pick x to be a vector that is a constant everywhere, say it's 1 everywhere, that's a feasible solution. And with this choice, all those differences are 0. So the numerator is 0, the whole expression is 0. And so this shows that actually lambda 1 is equal to 0. So let's prove the first non-trivial result from the fundamental theorem of spectral graph theory. Let's say that we have some graph G, and that this graph has at least k connected components, so that we can divide the vertices into k subsets C1 up to Ck with no edges between them. Recall also that lambda k of a matrix can be characterized as the minimum over all k-dimensional subspaces of the maximum for non-zero vectors in S of the Rayleigh quotient of the matrix. As we computed before, will be the summation over all edges of xu minus xv squared, and then this will be divided by d times summation over v of xv squared. Now let's define S to be the linear subspace of all vectors that are constant on connected components of the graph. So S is the set of all vectors x, such that for every component and for every two vertices in that component, x takes the same value at those two vertices. Now S is a k-dimensional space, as we can see by noticing that the k indicator vectors of the k connected components are linearly independent vectors, and they are all elements of S. So this is a k-dimensional space, and for every x which is in this space, when we look at the numerator of the Rayleigh quotient, obviously it's a summation over edges of xu minus xv, which is always 0, because every edge must be entirely containing one of the connected components, and then if x is in S, the value of x at the two endpoints will be the same. And so we have a k-dimensional space for which this maximum is 0, and so this shows that lambda k is smaller than or equal to 0. It actually has to be equal to 0 because all eigenvalues are greater than or equal to 0. For the other direction, let's say the lambda k is equal to 0. So that means that there must exist some k-dimensional subspace such that every element of S has a 0 Rayleigh quotient. So in particular, the numerator of the Rayleigh quotient will have to be 0. But this means that for every x in S, when we look at every edge in the graph, x must have the same value at the two endpoints of the edge. So this also means that for every u that is reachable from v, we must have xu equal to xv. So this also means that if we have the value of x at some representative from each of the connected components of the graph, we can figure out what the value of x is everywhere else. And so this shows that the dimension of S is smaller than the number of connected components of the graph. And so the number of connected components of the graph has to be greater than or equal to k. So now let's go to the larger eigenvalue. Just by an analysis similar to the proof that lambda 1 was the smallest value taken by the Rayleigh quotient over all non-zero vectors, it's also possible to show that for every real symmetric matrix, the largest eigenvalue is the maximum of the Rayleigh quotient over all non-zero vectors. So since L is a real symmetric matrix, that means that lambda n of the Laplacian is going to be the maximum of its Rayleigh quotient. And 2 minus lambda n is going to be the minimum for non-zero axis of 2 minus the Rayleigh quotient. Remember, L was the identity minus 1 over d times the adjacency matrix. So this will be just the identity plus 1 over d, the adjacency matrix. We can follow the same calculations that we did to get an S expression for the numerator of the Rayleigh quotient of the Laplacian, essentially having a plus instead of a minus in the same calculation, and then see that the numerator of this expression will be 1 over d times the summation over all edges of xu plus xv squared. And we have this identity. So now 2 minus lambda n will be the minimum of this expression that has sum of squares both at the numerator and the denominator. So this will always be greater than or equal to 0. And so this shows that 2 minus lambda n is greater than or equal to 0. So lambda n is smaller than or equal to 2. Now let's say the lambda n is equal to 2. So that means that there exists some vector x such that that modified Rayleigh quotient that we looked at was equal to 0, such that the summation over all edges of xu plus xv squared is equal to 0. So this means that for every edge uv, xu is equal to minus xv. And x is not everywhere 0. So let v be some vertex such that xv is non-zero. And let's consider the partition of the set of vertices into the following 3 sets. Let's call A the set of vertices that have the same value as xv, B to be the set of vertices whose corresponding coordinate in x is equal to minus xv, and C the rest. So now I claim that A union B is a bipartite connected component of G, and that AB is its bipartition. So let's say this is the whole set of vertices, and that this is A and this is B, and the rest of vertices are C. Let's look at every possible edge in the graph. For every edge, the value of x summed at the endpoint must be equal to 0. So this means that it is not possible to have an edge entirely contained into A, because otherwise the sum of the endpoints of the edge would be 2xv, which would be different from 0. So there is no edge entirely contained in A. Also, there cannot be an edge from A to C, because then it would again not be true that the sum would be equal to 0. We can definitely have edges connecting A to B. We cannot have edges entirely contained in B or going from B to C, and then maybe we can have edges entirely contained in C. But when we look at B union A, that's disconnected from the rest of the graph. It could also be the whole graph, because maybe C is empty. And it's bipartite, because every edge in A union B has one point in A and one point in B. So actually, we didn't prove that A union B is connected, but we proved that it's disconnected from the rest of the graph, so it's a union of connected components, and that it's also bipartite. So if A union B is not connected, each of its connected components is going to be bipartite. So definitely G contains a bipartite connected component as promised by the theorem.